Hello developers, let's start developing. So, we're back to the task that we missed from the 2022 advent of code, and we are already in 2023. Today is the 1st of January, so in the next couple of days I will be focusing on the task that I didn't have the time to solve before the holidays, that I was kinda busy, and to be honest, the tasks that were too hard for me to solve immediately. So, speaking about hard tasks, the first hard task we run up against is task 16. What is the story here? Well, we have some kind of a situation when we need to open some valves. We have some kind of a map, let's call it like this. We have several valves, each has a flow rate of 0 or non-zero, and it has a set of tunnels that lead to other valves. The question is how many valves we can open, how much pressure we can release in 30 minutes. And we are giving a scenario. It takes a minute to open each valve. It takes a minute to walk between two adjacent valves. And that's the situation that we're in. And we have a herd of elephants when we are actually trying to save. How did we have elephants inside the volcano? It's not really explained, and it's not that I actually know or care. So, we have that situation. And what I initially started to do was basically have run a full simulation, all the possible paths. So we're starting from valve AA, so that means that we can go to these three valves, or we can open this valve. It doesn't make sense to open it because it doesn't release any pressure. So we have three scenarios, and after that we have from DD, we have three more scenarios, but this has a non-zero flow rate, so that means that we actually have four scenarios. So that means that this keeps multiplying and multiplying and multiplying and multiplying. So that's the initial approach that I tried. And I have a video where I take this approach that will never see the light of day because it failed kinda totally. This basically runs a simulation, and we're also having some kind of branch pruning approach because, for example, if from AA we go to DD, it doesn't make sense to go back to AA without doing anything. That would just waste 2 minutes. So even with some analysis of all the invalid paths that are available, let's actually run this on the small demo input. So after the first minute, we have something like 3 paths, 6 paths. In the 27th minute, we have 34,000 paths. In the 30th minute, we have 50,000 paths. So 50,000 different paths are available, and we're going to evaluate each and every one of them. And we're going to get that the maximum pressure released is something like 1600 pressure units or whatever. But let's see what happens when we change this input for the much bigger input. And note that I'm starting node with a special flag that enables it to use up to 16 gigabytes of RAM. The usual value is something 1.5 gigabytes. This version uses about 16 gigabytes, and I will just take my input, my real input, which looks like this. You can see there are a few more valves. And let's just change it here. Let's see what happens. So we are branching a bit faster. At the minute 17, we already have 150,000, minute 18, minute 90. Let's see what the task manager says in minute 19, where we have a 500,000 paths, different paths. and node is using some about a gigabyte of RAM. Wow, Chrome is using loads of RAM for something. I will need to take a look into that. But this number just keeps growing and keeps growing and keeps growing, and we're getting to minus 21 when it's 1.5 million. And 15 minutes later, we have this. So, even using 16 gigabytes of RAM, we got up to minute 25 when we had something like 15 million different paths in minute 25, and then we basically just ran out of memory. I tried this with 32 gigabytes as well. It just took a lot longer to get to this point, but it basically ran out of memory and died. So this is not a viable path. At the very least, it will be extremely slow. So what can we do? What was my mistake here? Basically, my mistake was thinking about the path. Since minute to minute, what path we're gonna take, because in those 30 minutes we're gonna do something. No, actually, this is intentionally, I think, misleading in the problem description, as it is even the example is given in terms of minutes and everything, and we have this all the valves are equal, but somehow just have zeros. Well, that's not actually the case. What we have here, we have some kind of a graph. When these are nodes and these are not nodes, these are just links between different nodes. So we have no need to be inside FF unless we are going from valve E to valve GG. I'm going to use single letters for this, for the valves. And similarly, G has no meaning unless we are going from EE actually to from valve E to valve H. And let's see how much valves do we actually have. We have 1, 2, 3, 4, 5, 6 valves. So we don't have 15 million different paths through these valves. Basically, starting from wherever, we can open. It doesn't make to be somewhere unless we're going toward a valve that we are gonna open. So we have a valve B, C, D, E, H, and J, 6 valves. So that means that we can open valve B first, then C, then D, then E, then H, then J, or B, then C, then D, then H, then J, then H. So we have 6 valves, so that's 6 factorial, which is not a good kind of complexity. Factorial is among the worst classes of complexities, but factorial of 6 is 120. So we have 120 in total different options that we can, different orders in which we can open the valves. Not, not actually 55,000. So most of these 55,000 paths are basically invalid. That invalid in the sense that we are not going directly from valve to valve. Go to a valve, open it, go to the next valve, open it, go to the next valve, open it, go to the next valve, open it. So, how do we fix this? Well, first of all, uh, let's see how we're gonna map the input. I already have this. So, this is what I used for the failed version. So we're gonna start with that because that part kind of worked. Let's remove everything up to here. Let's remove this as well. We don't have anything. We don't need anything. Let's just replace this with return 0. or -1. And I will actually set that this task is the one that we're gonna run. So we're not running 16 failed, we're running just plain old day 16. They should just get a -1. So how are we parsing the input? Well, it's simple. This should be a simple regex. When we extract the valve name, the valve float rate, and the valve's neighbors. After that, we just split the neighbors on a comma space, and we have a list of all the neighbors. After that, we have a map, and we have our volcano, which is a map of a string that is a name to an input valve. And an input valve has a name and a flow and a map of neighbors. So first thing that I'm gonna do, I'm gonna separate this. Not all valves are created equal. So I'm gonna have an interface called a type actually called cell, which will be either a valve or a corridor. So what is a corridor? Well, a corridor will have a name that's a string. It won't have flow. And I will add something called type corridor. And I will add this to the valve that has a type valve. Something along these lines. And then we have a type called valve, we have a flow that's number, and then we have a list of neighbors, and this can be a simple string array. We don't need this, and we have that this is exactly the same, but it doesn't have a flow. So this, we could design this better. We can extract the type, the name, the neighbors, and everything aside from this, but I like that this design kind of makes it obvious that we are dealing with two different things. We cannot get the flow of the corridor because a corridor doesn't have a flow. And that's a fundamental difference in how we're thinking about our data. Sometimes it makes sense to go the other way, to just say, oh, a corridor is just a valve with a flow of 0. This time we want to do the other thing and say that not every cell is a valve. So we will have a list of cells here. And yeah, we don't have the type, so we're gonna have to do something else. And we'll say now, so let's find the flow. That's this much. And if we don't have a flow, is 0, then we're gonna return a corridor. The name is match of 0. Yeah, those are the neighbors. And otherwise we do have a flow, and we're gonna return what we previously returned. We have the name, we have the flow. We're missing a parenthesis here, so that's not a major thing, and we're gonna add another here. And we have our name, our flow, and of course we're gonna add the type that this is actually a valve. And after that we can just have them into a map. Transform them into a map instead of an array, and we have our input. Let's just log it here. Let's call this a volcano. Let's see what happens now. Yeah, these are our valves, and we see this is a corridor. I will change to the small input so that we can see more clearly what is happening. So we have AA is a corridor, this is a valve, this is a valve, this is a valve, this is a valve. These are corridors right now, F and G. So I will use this data to transform it. First of all, I'm only interested in the valves, in the order that we're gonna be looping through the valves. So it might make sense to have a variable that's called like this. And yeah, it's gonna be something like this. Filter out the valves. These are the valves. Now, I will be interested, since I will only be going from a valve to a valve, I will be interested in how far two different valves are from each other. Because we're not going to be going through these two unless we're going from here to here. So we need to know that from E to H we have 1, 2, 3 minutes of difference, and so on. So each time we're moving somewhere, we're moving from a valve to a valve. So for that, we will need to know the distance between two valves. So we will have our distances. We will want to have something like, first of all, let's create a method that called get distances that will give us a distances. Yeah, that could be a that inside the volcano for a certain valve or for a certain cell. Doesn't really matter. How do we do that? So what will be our... Oh, we have some kind of a suggestion already. Let's accept it and go through it. I might not... this is a map of a string to a number. Yeah, that's good enough. So our distances is thing that maps from from the name of a cell to a number. That means to get to that cell, we will need to do that. So we have we're setting that we are 0 steps away from ourselves. Yeah, that makes sense. We're setting that a queue where we are, and we are getting the current distance. We're getting the current cell, and for each of the neighbors of that cell, we know that those neighbors are one away from the cell. That's the definition of a neighbor. And if they're not already in the map, we have to have this check, because if we are able to get to one cell from one side in a distance 1 and from another side with a distance 5, we're always going to choose the 1. It doesn't make sense to choose the 5. Yeah. So this will work. So what we can do, we can have our distances as a new map of not string number, but a map of a string and a number. So this is a second order number map, which is a map of maps. And now for each element in the valves, yeah, get the distance and set it over there. And I will want to have one more distance here. So distances, not that, but I will want to have the distances from AA to all of the others, because that's where we're starting. Because we have a zeroth move when we get from AA to our first valve. Let's see how that looks like. It's not gonna look like anything because we didn't log them. Log the distances. And they should be correct. So we have from B to B is 0, to C is 1, to A is 1, to D is 2, to H is 6, 6. Kinda looks correct, but I have a bit of a problem. We are moving to 10. It doesn't make sense to move from BB to AA. That's an invalid move because we should be moving from a valve to a valve. So we're not pushing the volcanoes here. We're only interested in distances to other valves. So we're gonna need to do a little more of work here. After we have that map, we're gonna need to get a list of corridors to eliminate them. That's an array of corridors, and actually we don't want them like this. We just need the names. Yeah, that's the corridors names, and then we can say for each of them distances dot delete the corridor. This kind of assumes that this corridor exists here, but as we've seen and as I've verified, the input is connected, so it's possible to get from everywhere to everywhere else. And one other thing that I noticed, that we don't really need this value. It doesn't make sense to go from B to B. In fact, we can actually go from B to B, but we're not doing anything. So we started with the start, but we're gonna remove it at the end. Let's see what we get now. If I'm correct, from B we should have only 5 items, and from AAA we should have 6 items. Yeah, so this is a map of 5. This is the 5 other valves that we can go to, and AA has a list of 6 valves that it can get to. We can get to D and B in 1 step because those are neighbors. C, 2 steps through B or D. E, 2 steps through D. J, 2 steps through D. J is 2 steps through something else, I think. Doesn't really matter. And then we have HH in 5. Because HH was the one with the low. Yeah. JJ, we are getting to J through I. And I only connects to A. Yeah. Okay, so this is our map of distances. And now we're just gonna, we can again do a brute force search through all of these things. And that is what we're gonna do. We're just gonna do a depth first search, a simple depth first search, and see if this runs fast enough. if the depth first search does not run fast enough, we will still need to do some kind of a logic between and maybe have a priority queue. But for 120, we will have a very fast depth first search after we have our distances. So we have our distances, and now we need the actual depth first method, and that's the easiest way to do it is to recurse on it. And we're gonna need the distances and we're gonna need the volcano. So I will make this as a function inside of this. So this is a function that will take our start position, where we are at the moment. It will take how long we have left, and it will take where we've been so far, what is open and when. And yeah, that will be, let's have that as a type. So a type of a open valve or a flow. Yeah, let's describe that, and that will have something like this. It will have a name that's a string, or it can be the valve. It will have a number when it was open, and for simplicity's sake, it will have a flow. So that means we are opening valve B on minute 7 or something like that. So we're getting the flows, which is an array of open valves, and we will be returning the next flow, which is gonna be an array of open valve arrays. Yeah, let's have it as returning an empty array. So, assuming that we have that, then the max flow is get the maximum pressure of starting from AA with 30 minutes left to spare and no flows open, get me the maximal flows. And then we're just gonna need to do for each flow, we're gonna need to do a sum. For each flow, for each open valve, we're gonna need to see how much pressure it will release. It will release, if it runs for 30 minutes, it will release 30 times that pressure. So yeah, this formula is correct. And then we're just returning the result. So if we run this, since we will return 0 items, we will have a clean and available 0 as a result. Did I remove the console log? Yep, I did. So this works. We are just have the simplest task that we need to implement the actual depth first search. So first of all, how do we know that we've hit our limit? If we're gonna run until we're out of minutes. It's not less than or equal. Yes, it's less than or equal. That means what comes in, that comes out. We are not able to do anything, and that's it. Otherwise, for this valve, get the distances. And then get the valve. Yeah, that might be useful. And now we need to open OW. And this is where AA causes a problem. So we cannot open AA. We can step this in two ways. And one is to basically call it once for all the valves that are available from AA. Say, imagine that this is first, this is second, but I'm just gonna write it here. So not as a valve, but if this is a corridor, then we're not gonna be returning flows, we're gonna be getting flows. Let's make this into a helper method. And weirdly, I will extract this away from part 1. Let's just call it get flows, and we're just gonna call it with a cell and flows. And now, if the cell is a corridor, we're not opening anything. Otherwise, we will add the flow of the cell to the open valve. Now, return flows and a new open valve, which is this, and it's open at, we're gonna need the minutes. Yeah. Minutes is gonna be a number, and that means that at that minute we are opening a cell with that specific flow. Does it make sense? It might. No, that's for later. So now we're gonna need to see next flows. What are the next flows? Are that much. So now we need to just a sec. Yeah, we might need this a few more times. So this happens if we actually open that flow at that minute. Where do we go next? So now we're gonna need to loop through all of the just a sec. If we're gonna need to loop through the distances, which kind of feels weird. Yeah, so yeah, let's do this, and then I will maybe refactor it a bit. So current distances, but this is a map, and we can iterate over a map, but the maps are returning. If we have X, the type of X is actually a tuple when the string is the key and the number is each value. So that will be the neighbor name, and this will be the distance of the neighbor. So for each of the neighbor, which is n distance away, we need to loop. We need to check first whether this neighbor is already visited. How do we know if it's already visited? If it's in the new flows. Or in the flows. Basically, because we're only maybe adding this one. If some of them is equal to the valve name, we're just skipping that one and continuing. Otherwise, we don't need the valve itself. We will need to see what happens if we go to that neighbor next, and let's get maximum pressure of our neighbor, our minutes from which we subtract the distance, and we subtract once more because it will take 1 minute to open it, and we are putting next flows, and that's the flow from the neighbor. And now we will need to do this. What is the value of the neighbor? It's gonna be the sum of that flow. Ah, this is gonna be what will be the maximum. This is gonna be a let. This could be made better. Yes, that's the max flow, that's the max value. And then we are getting the n value, and if n value is over max value, then we're doing something stupid, and that's actually setting these two values. So, and at the end, we're just returning the maximum of that. And this will basically drill down inside the possible tree of things, and hopefully come back with the correct number. This is kinda hard to debug, but we got our answer 1651 in 72 milliseconds. Which means that fortunately we had no errors in the DFS. So let's try it with the bigger input. Let's be sure that we're actually getting the whole of it. It ends with JR. Yeah, that's it. Yeah, and let's see now if it will run fast. Oh, and it ran very fast. It ran in about a second and a half, which is a bit of an improvement on 15 minutes that didn't finish. Let's see if 1845 is about the right answer. That's the right answer. Yeah, we are getting 1 gold star. And as for the second part, I've already seen it, and it's very interesting, and it's quite a big complication on this. We will solve this in a separate video, and this will require us to do all the branch optimization with priority queues and analysis of the DFS, so that we can solve this with the DFS, since it is that kind of a problem, but we will solve it in a relatively sane way. So we have an extra star. We're at 36 stars at the moment. This is solved in an acceptable time frame with an acceptable approach. We are just analyzing all the valves. We are running this. We can add a call count, for example. How many times was this actually called? It should be a lot. Let's say we have a call count at 0, and we have we're incrementing it, and after we get the result, just log the call count. So how many calls did we have of this method in this 1 second and a half? Well, it's this number. We had 1,200,000 calls. Note that each of these numbers was increased by 1. We started from 0 and we counted by 1 until we got to this 1,230,000. So this was quite a heavy computationally task, but it runs in a reasonable amount of time. Part 2, with this approach, won't run in any kind of reasonable amount of time. So we will have to optimize. And then we might go back and optimize part 1, but that's a story for another video. For now, don't forget to like and subscribe if you got to this part of the video. And keep developing.